Hello, welcome again. We are solving IITJ physics. The topic is dual nature of radiation and matter. Question number 5 is given figure shows few data points on a photoelectric effect experiment for a certain metal. The minimum energy for ejection of electron from its surface is Planck constant is H is 6.62 minus 34 joules second. So this is your V stopping potential and this is your frequency on x-axis, and this is point A, B and C. At a point A, only the x coordinate is given, and at point B the x and y 5.5 and 0 are respectively, and at C these are 6 and D. So now the options for minimum energy of ejection of electron is 2.27 electron volt, option 2 2.59 electron volt, and option 3 1.93 electron volt, and 4 2.10 electron volt. So here the point A represents the stopping potential because at point A the negative y coordinate is observed, because at point B the y coordinate is 0, and so as A is below the A is below B, so it will have a negative y coordinate. Okay, so this is your stopping potential. So at point B the stopping potential is 0. It means the electron will have minimum energy at this minimum energy is required for the ejection of electron. Okay, so the energy is given by this h into frequency, where h is Planck constant and f is your frequency. Okay, so this is the minimum energy required for ejection. Okay, and this is given as so h is your 6.62 into 10 power minus 34. That value is given, and if it's not given, you have to remember is okay, and f is your 5.5 into 10 power 14. Okay, so the energy, this is in terms of joule, and in terms of electron volt, we divided by 1.602 into 10 power minus 19. So it comes out to 2.27 electron volt. So option 1 is the right answer. Next, particle A of mass ma is equal to m by 2 moving along x-axis with velocity v dot collides elastically with another particle B at rest having mass mb is equal to m by 3. If both particles move along x-axis after collision, the change delta lambda in the Broglie wavelength of particle A in terms of its de Broglie wavelength lambda 0 before collision is option 1 delta lambda is equal to 4 lambda naught to 2 lambda delta lambda is equal to 5 by 2 lambda naught, 3 delta lambda is equal to 2 lambda naught, 4 delta lambda is equal to 3 by 2 lambda naught. Okay, so here the mass ma has mass is equal to m by 2 and initial velocity as v naught. Okay, so and the mass mb has the mass of m by 3 and initial velocity 0. So let va and vb the final velocity of mass ma and mb. So then this is your initial momentum and this is your final momentum, m by 2 into v naught plus m by 3 into 0 plus is equal to m by 2 into va plus m by 3 into vb. Okay, so these are the initial momentum. Now we can omit m from it, so that will be v naught by 2 and va by 2 and is equal to v by 2 plus vb by 3. So this is equation number 1. Now as it is given that there is they collide elastically. Okay, the collision is elastic, so the coefficient of restitution is 1. So the relative velocity after collision divided by relative velocity before collision is coefficient of restitution. So this is your 1, and actually the coefficient of restitution given by the velocity of b minus velocity of a divided by this is the final velocity difference, taking b first and a will stack from b. Okay, and whereas for final order relative velocity before collision, we'll take A first. The velocity of A, initial velocity of A is v naught, and velocity of initial velocity of B is 0. So we'll take A first, v naught minus 0, so that will be v naught. Okay, and from this we have VA minus VB is equal to minus v naught. Okay, so this is equation number 2. Now we can divide this equation number 2 by 3. Okay, and subtract it. So it will be v naught by 2 minus v naught by 3 is equal to VA 1 by 2 plus 1 by 3. Okay, so because VB by 3 will cancel out. Okay, so from this we have VA is equal to V naught by 5, and the d Broglie wavelength is your h by momentum. So initially the lambda naught is h by mv naught by 2, because v naught is the initial velocity and mass of m is m by 2. So this is your initial de Broglie wavelength, and finally the de Broglie wavelength is when we divide h by final momentum, and final momentum is m by 2 into VA, and VA is final velocity, and VA found out as v naught by 5, so it will be your 10h by mv naught. So the change in de Broglie wavelength is delta f minus delta lambda f minus lambda naught, that is delta lambda, that is then minus 2h by mv naught, or 8h by mv naught. Delta lambda is equal to 2h by mv naught into 4. Okay, so it is as lambda naught is 2h by mv naught, so it is delta lambda is 4 lambda naught. So option 1 is the right answer. Okay. Two sources of light emit X-rays of wavelength 1 nanometer and visible light of wavelength 500 nanometer respectively. Both the source emit the light of same power of 200 watt. The ratio of number of density of photons of X-ray to the number density of visible light of given wavelength is option 1 1 by 500, option 2 500, and option 3 254 1 by 250. So number density of the photon is number of proton per second. So this is given by P by H into V, frequency, and frequency is given by C by lambda. So for first beam it is P by H C into lambda 1, and for second it is this. So ratio is lambda 1 by lambda 2. So ratio is n1 by n2. Lambda 1 by lambda 3, lambda 500. So answer is option 1.